Hi everyone, welcome to week 7. Getting closer now. I hope everybody had a good week. We are going to look at solubility, and it follows along the same vein as the boiling point, melting point, and volatility. I'll explain why. I'm sure you'll get sick of me repeating myself by the end. This one will be a bit shorter than the others because it's not hugely in depth and it's really just repeating what's already been said, but just relating it to solubility. So there's a few. So solubility, organic compounds, is all determined by the intermolecular forces, which we're going to go over again. Hopefully, if I keep repeating it incessantly, you will never forget it. Let's have more set up the story. Moved everything. So, I'm sure you're sick of me saying the words intermolecular forces, but in order to understand organic chemistry, it's what you have to understand. So, we have, I'll get rid of the share so you can see. Okay, now it's gone way too close. That's being denied there today. So, we have dispersion forces. Baby crying in the background. He is got an earache. Fun all round today. So dispersion forces are present in non-polar molecules. So dispersion forces present in non-polar molecules. So we know that happens when we have a covalent bond. No significant, let's see, no significant electronegativity difference. So no significant electronegativity difference between the two compounds. So we look at hydrocarbons, carbon and hydrogen bound together. Assume they're sharing the outer shells. And on this side, let's say the electron's over here. At some point, the electron will be over this side. So over this side will be negatively charged, this side will be positively charged. And then we have another hydrogen, which over this side, on this molecule, the electron is over here, and you get an attraction through there. Low boiling point, low melting point, high probability of volatility. So we know that if we leave, when you pour in petrol, you can literally see it volatilizing as it's coming out of the nozzle. So, anes, enes, and ions have these dispersion forces. So then we move on to dipole-dipole. dipole forces. So dipole forces present between covalent, well, there's a covalent bond between, we have a polar covalent bond, in this case between carbon and oxygen. So this is the ketones, aldehydes, and esters. So this is when occurs when oxygen is a lot more electronegative than carbon, so it hogs bonding pairs of non-bonding pairs of electrons, making oxygen negatively charged and carbon positively charged. And then the reason that it's stronger, this is the second strongest, is that the dispersion forces, that negative charge swings around to the other side really quickly, whereas this is slightly more permanent. I'm going to spend too much time because we are just rehashing. Okay, so the third one, hydrogen bonds. Hydrogen bonding, again, covalent bond, it's polar, and hopefully you remember that it occurs when hydrogen is bonded to oxygen, nitrogen, or fluorine. And the reason that it's special is because these three are so electronegative compared to hydrogen that it creates an almost permanent dipole. So if we have hydrogen and fluorine, this extra electron is almost always on this side, and this side is always positively charged. Again, we won't spend a huge amount of time, but if you see hydrogen bound to oxygen, nitrogen, or fluorine, it's an alcohol, amine, amide, or carboxylic acid. So, the reason that this matters, I'm going to go over the basics of solubility, is, I think it should be unit 2 for year 11, solubility, if I remember correctly. So like dissolves like. What this means is that you have to have the same intermolecular forces present in two liquids for them to dissolve together. So if I have petrol, so octane, and I try to mix it with water, it's not going to happen. If you spill oil on the ground and you try to spray it around with the water, you'll just spread the oil even further. Because water has hydrogen bonding, and dispersion forces. So this is why I keep drilling in the intermolecular forces, and it will follow through to next week as well. So, like dissolves like. Dispersion forces, hydrogen bonds, cannot dissolve each other. So, polar bonds can dissolve polar bonds, non-polar bonds cannot. If you pour oil on the ground, best thing to clean it up with is petrol or something similar like that. So, quickly going over solubility, we can look at, so solubility increases with temperature, solubility increases with pressure. This is for liquids only. So increase in pressure, you increase the solubility. And remember, like dissolves like. We also have this concept of saturation. So you add salt and water. Eventually you get Na and Cl dispersed as an aqueous solution in water. But eventually you can't dissolve anymore. So that's saturation. Everything has a saturation point. What we have, sometimes we can get a super saturated solution, which allows you to go beyond that point. And I won't go too much into that because that is regular chemistry, but it just gives you an idea of more background on solubility. So solubility is completely determined by the IMF present, chain length, so the length of the carbon chain, as well as the shape of the molecule. So they are the things that determine, but the major one is this. This determines what is soluble in what, and these determine how much of something is soluble in something else. So if you're following along the slides, we have the solvent plus the solute so the solvent is what is the dissolver. The solute is what you're wanting to dissolve. And the solution is the final product. So the solute dissolves into the solvent to produce the solution. So salt, water, salty water. So looking at this slide that says rule of thumb, we look at like dissolves like. We have this term insoluble. And this refers to things that cannot dissolve. So oil and water, oil is insoluble, or these two are said to be immiscible in each other. So, when we're looking at solubility, we need to look at the polarity. So, is it a polar or non-polar bond? If you see carbon bound to oxygen, then you know it's a polar. Or if you see carbon to hydrogen and nothing else, there's no other bonding present, then it's non-polar. Okay, we see this, but then we also see an OH bond. So this is where we would check for hydrogen bonding. So we check for hydrogen bonding. This will tell us what this particular thing you're looking at, molecule you're looking at, will dissolve into. So, we look at hydrocarbons. So, we know that they only contain carbon to hydrogen bonds. So there is only dispersion forces present. So this will not dissolve in water. We refer to water as the universal solvent because it can dissolve everything else aside from hydrocarbons. So hydrocarbons and water are immiscible in each other. So anything that's an ane, or ion will not dissolve in water. So they all will dissolve in non-polar solvents, though. All of these hydrocarbons. And what happens is, when we have dispersion forces and another set of non-polar molecules next to them, what happens is, so we have call this pentane. So they're all nicely packed in together, happy days. And then over here we have octane, which is also a non-polar solvent. So what happens is that when you put these together, all of these bonds effectively break. And then we get a reforming over at the bottom here. Turned pentane in green. So now they're all mixed uniformly together. And they've all bound with each other. So this is why they have to have the same intermolecular forces. Pentane mixes with octane, and they share the bonds, and everybody is happy. So if you think you put them together, all of these bonds dissipate, and then they join back together. And in that joining together, they become one liquid. So we're on slide 11 now. So liquid hydrocarbons are very, very good for cleaning. So degreasers, so often made of hydrocarbons. Anything that's used to clean up oil is usually a hydrocarbon, a liquid hydrocarbon. So greasing oil on your driveway, you can try and get it off with a gurney, but all you're really going to do is move it around. Find a liquid hydrocarbon, dissolve it, and spray the hydrocarbon away. Not that great for the environment, but that's how you can do it. So, haloalkanes, I haven't really gone through them, so I'll give you a quick. And what they are is they are alkanes that have a halogen attached. So we might have ethane, but instead of a hydrogen here, we have fluorine. So that's what a haloalkane is. Might be a better example, might be chlorine or bromine. Now, this is where it gets a bit fuzzy, although the haloalkanes are almost the same as hydrocarbons. This bond here is actually slightly polar. So they are a polar molecule, but they're not very polar. The polarity is weak. And they're only a little bit, or what we call slightly soluble in water. So haloalkanes, it's an alkane, but a hydrogen hydrogen has been replaced by a halogen in group 7, hence the name haloalkanes. This bond here between the alkanes and carbon is slightly polar. So, but it's not very polar. So it's only slightly soluble in water. It's one of the few occasions where in chemistry we use vague terms, so slightly, very, barely, sparsely. Words used to describe solubility. Any of these haloalkanes that are denser than water will settle. They will not dissolve, and they will settle to the bottom. Obviously, being heavier than water. So, aldehydes and ketones. Never mind the rude interruption. Oh, you can't see. Never mind. So, aldehydes and ketones. So, they can't form hydrogen bonds with themselves. And you can see there that they have a carbon, oxygen, double bond. And then we have water, which has its hydrogen bond. And we get hydrogen bonding between the hydrogen and oxygen. Remember, when we see hydrogen bound to oxygen, nitrogen, or fluorine, we get hydrogen bonding. So that, even though these aren't these molecules, if we look at aldehydes and ketones, they are not, they don't produce their own hydrogen bonds, but they can produce them with the spare hydrogen on water, which makes them soluble in water. So very soluble in water. So hope you're seeing the pattern again with intermolecular forces. And the thing with aldehydes and ketones is the smaller ones, so as in backbone chain length of carbons, are really soluble. The bigger are less soluble. So smaller aldehydes and ketones, more soluble, bigger ones, less soluble. And this is because this carbonyl group interacts with water. And the longer this chain is, the less interactions we see with water as this carbon spline gets longer, and the longer molecules are less soluble. So again, you can see there that we use very ambiguous terms: very soluble, soluble, and slightly soluble, as opposed to hard and fast numbers. Solubility varies so much depending on the condition. So, when we're talking about hydrocarbons, so when we talk about aldehydes and ketones, the longer the backbone, the less soluble they become. Hydrocarbon, the longer they are, and the same thing with boiling point and melting point. There's more space for these dispersion forces to act. So smaller, bigger, more soluble. So now we look at So now we look at the alcohols. Alcohols and carboxylic acids. Again, we have hydrogen bonds, so alcohols is so you get hydrogen interaction between the two. So again, smaller the molecule, the more soluble something is. So when you're talking about hydrogen bonding, smaller molecules more soluble. So small molecules are more soluble in everything except the hydrocarbons. Again, we learned last week that the carboxylic acids are different because they have two sites for hydrogen bonding. So if we look at carboxylic acid, it has two sites where it can create hydrogen bonds with the water, because we can have so we have two sites for hydrogen. And now it's said that carboxylic acids have, the smaller ones have an unlimited solubility in water. So again, carboxylic acids, hydrogen bonding. The smaller the chain, the higher the solubility. So that was fairly quick because solubility is fairly basic. If you remember those rules, hydrocarbons, the bigger the chain, the more soluble. Everything else, the smaller the chain, more soluble. And like dissolves like. So questions are, what affects the solubility of a molecule? And how does the shape of the molecule affect the solubility? So just to explain that better, so the first one is the what are we, let me start that again, put these slides around that way. The question is, what are the key variables that affect the solubility of the molecule? And I'm going to explain the last one. So the molecular shape. We saw with boiling point that straight chain molecules had a higher boiling point than branch. Whereas branch molecules are more soluble. Straight chain soluble. So when you've got two straight chain molecules, there's lots of dispersion forces, and it's hard to overcome those dispersion forces to force two liquids to come together. Whereas in the chains, if they're sort of bound like this, and there's just one dispersion force in there, then it's easy to overcome that and bond it to the solvent, say if it's water. So branch chain molecules are more soluble than straight chain. Again, a few rules from a lot of rote learning in organic chemistry. So I will see you guys throughout the week or next week or later on in the week. And we're getting to the point here now. So next week and the week after we'll probably go over an hour, maybe. So I'll